Right. Can you hear me well? Yeah. Good morning, and thank you for turning up. I actually thought the audience would be much more sparse this morning than it is. So thank you very much for being there. So I'm going to present to you this work, which I did in collaboration with Laurent, who is right here, as well as Vincent Skelkens, who was a PhD student of Laurent and now works in Paris, and Laurent Daudet, who is from a small startup in France that has developed a very interesting tool that we are going to talk about in just a minute. Yes, so I'm going to talk about signal processing after sketching. We're going to go through a brief explanation of the problem statement. We're going to talk about a little bit of maths, a little bit about this mysterious machine that can do sketching very easily, and a little bit about the main results. And we'll close off with some experiments to demonstrate why we think that what we did is kind of useful sometimes. Okay, well, let's get into it. The context of this work is signal processing, and what we are trying to achieve is to say, okay, if you have some signals and you do some sketching on it, so we're going to explain this. But if you have your signal, you sort of squash it down and chew it, and then you want to do some processing after it, is it possible? And if so, under what conditions? So what we want to try and do is estimate functions of the signals after doing a projection, a random projection. But what we could do is to come back to the original signal, do our estimation, but that wouldn't be too interesting. What instead we're going to try to do is to say, well, you have your signal, you go into the sketch domain, so you sketch the signal, and you're going to try and estimate things from this. And there are a number of potential applications, such as event detection or localized, trying to find localized information about images in a video stream. So to put this in a sort of a more visual way, so imagine you have some a data set which has many vectors of potentially very large size that you would like to reduce in terms of dimension, because if the dimensionality is too high, then it becomes a little bit too difficult to handle. What you have in this case is some sort of operator, projection operator, psi, that you can see right in the middle there. And with this projection operator, you're hoping to try and get the dimension down. The problem is that when you do this, and imagine when you get your data, you do this immediately, so you never really have access to your x's. You only get a sort of a transformation of this, which is the y you see on the right in the green bubble. So this y is what you have access to, and you only have access to this. And this comes from real data that exists somewhere, but that you don't necessarily have access to. And what we want to do is to try and estimate some sort of function, as you can see down on the left there, which is the scalar product between some vector u and the instance xi. So you have the x that you're interested in, and you want to try and find information about it that will take the form of a scalar product between u and xi. So, for example, if you look just under the red bubble, you have the an image of the famous image of the camera guy. And if you're interested in having, for example, the average of the image inside the green square on the right, so say you just want to see what's inside the most important part of the image, what you could do is say, well, let's take a vector u that is 1 inside the green square and 0 outside, the average of the image. So in this work, when we talk about signal processing, we talk about a scalar product between the signal of interest and another signal that you design for a particular purpose. And the question that we are asking here is, if we have some transformation psi that takes an instances and maps it to something else in another world, is it possible to find a function that will take the transformed instance, the vector u that you design according to what you want to do, and the operator psi, such that we can approximate some function of the scalar product between u and xi? Now, the function f does not necessarily need to be too complicated, but depending on what the projection operator is, it might change a little bit. So To give you a brief, slightly more detailed example, this is the parking lot outside our office. Imagine you have a camera that monitors it, and you want to know whether your usual parking spot is free or not. But the camera is special. It takes the images and transforms them directly with this projection operator that I call B here, which is the side that was in the previous slide. If you take the whole image, and if you look at the picture on the top left, your parking spot is free. But if a car comes and parks on the one to the left, now I'm sorry about the black car, it's very ugly, but I didn't have a better image of a car, and I didn't want to wait for someone to come park here. So if that happens, the two images are different, but your parking space is still free. But if you compare both images without more information, the only thing that you can conclude is the picture is different. Maybe my parking spot is taken, maybe it's not. Whereas if you were capable of estimating information such as the average, for example, in the green square, which is the picture on the right, well, in that case, you have access to just the information that you need, and you can see that your parking spot is still free. So a little bit more about this operator psi. So psi is a projection operator. So that means it takes the instance from one world, the real instance, nice and easy, that we can visualize, and maps it to another object in another world, which might not make much sense for us. So you can't really visualize this anymore. So this is exactly like compressive sensing. So compressive sensing is one particular example of psi, but there's others, and we are going to talk about this in just a minute. And the purpose, as I said, is to reduce dimensionality. So for example, if you have a video stream of very high quality, well, this is going to eat a lot of memory. Whereas if you project them into a space with low dimension, then it gets much easier to handle. And there are plenty of ways you can use this in industrial processes, for example, or you can imagine if you have lots of surveillance cameras in one place, but you're only interested in certain areas of the image, that could be a potential application. So this idea works well if psi is the classical compressive sensing operator. So in normal compressive sensing, the operation psi is simply you take your vector x and multiply it by some matrix phi, which is usually just a random matrix, a Gaussian matrix, for example, and that maps it to a new space of dimension m. In that case, it is totally possible to estimate the scalar product on the bottom left, and in this case, f is simply the identity. So with some filters, you can do this very easily and find exactly the scalar product that you're looking for. And this was done by Davenport and others in another paper, which was the inspiration for this. Now, for us, we're going to focus on something slightly different. Instead of taking psi as a linear operator, we're going to take a quadratic operator. So instead of the only difference is that it's no longer linear, it's quadratic. In this case, is it possible to find a function g that will approximate some function of the dot product on the left? And the answer is yes, we are going to see why. And in this case, f will just be the squared function. Right, so let's dive into the maths behind it. So the main thing to understand for the mathematical tools is that instead of using a simple linear projection with a matrix multiplied by a vector, we are going to use what is called rank 1 projections. So rank 1 projections, they simply take a vector of the same size as the instances, so a vector in Rn, a Gaussian vector, random vector, and if you start with a matrix, and we'll see why just in a minute, but if you start with a matrix X of size n by n, you're going to pre-multiply it and post-multiply it by the vector A on both sides. And this will be equivalent to a scalar product between the matrix X and the lifted matrix from the vector A, which is just a linear operation. Now, if you look closely on the left of the scalar product, A transpose times A is a rank 1 matrix, which is why we call this, which is why it is called a rank 1 projection. So this was actually done by Tony Kai. I forgot to put the reference on this about 10 years ago. Now you can do the equivalent transformation for a vector X, which is exactly the same thing. So if you take vector X and a collection of vectors A, and just one vector A, you do the dot product between A and X, so AT times X, A transpose times X. You take the square of this. And this is, if you expand the square, you find that this is exactly the same thing as the matrix version that we described in the second point. Now, that is one measurement. Now, if you take instead a collection of measurements, you're going to take M vectors A, so M random vectors, and do this product, dot product M times, and take the square every time. So this is the operator that we're going to focus on. Now, this operator is nice, but it has a few problems that make it technically difficult for us to handle, because since it is quadratic, there's a square in it, it only outputs positive measurements, which means that when you take the expectation of this, it's not centered on 0. This would make it more difficult for proofs later. So instead, we considered the D-bias operator, which was introduced by Chen and others in 2013. Which we call B, the famous B that I talked about in the parking lot example. And B simply takes two transformation, two rank 1 projections of size M, and takes the difference between the two. So it's nearly the same thing. You just take the difference between two measurements of rank 1 every time. So the A is exactly what we described in the previous slide, and you just make a difference between the two, and that centers B on 0. Now, the really cool thing is that this is something that you can do optically. So we're going to talk about this in much more details in just a second. But if you transform X to be a binary vector, then you can approximate the operator A, so the rank 1 operator, with an optical machine that has the advantage of not caring about how big X is. So this has a time complexity that is basically negligible because it's optical. It sort of codes the instance onto a light beam, and light travels at the speed of light, so it's very quick, and it's going to be very useful for transformation. So this machine is called an optical processing unit, and now we're going to see how this actually works. So what happens is you take your instance X that you have already binarized, that needs to be binary. It's a strong supposition, but we can work around it in many ways. And the machine accepts vectors of size up to 1 million, which is good enough. It can potentially go higher, but that will take a little longer. And the machine encodes the binary vector onto a light beam. So this works like. So there's a laser that comes into a crystal that makes it onto a sort of a light plane that gets reflected onto a mirror array. So every mirror is either on or off, and that sends a binary image through scattering material. So you can put it somewhere in this mirror here, which outputs a light beam of zeros and ones. So your instance is here inside this thing. And then what happens then is that the light gets sent through a scattering material here. So this is just a sort of layer of paint. I think it's the thing they used. And then what the output of this light beam is recorded by a camera on the other side. There you go. And so this has been measured by the people at Lighton. So Lighton is the name of the startup that developed this thing. They're also doing lots of natural language processing at the moment. And the output is models a rank 1 projection. So if you remember well, this thing here is exactly a collection of rank 1 projections, a projection of the vector X. Now, the really cool thing, as I said, is that this happens at the speed of light. So the beam goes in, it comes out straight away. And that means it doesn't matter how big X is, this will happen instantaneously. Now, of course, like all physical models, it doesn't work so well in practice. So it's not quite a rank 1 projection, but instead it's a quantized version over 8 bits. So you don't have like a full real number, you get integers of 8 bits that come out with the addition of a noise term, because of course there's always noise in physical processes, and a small gamma factor that's just an intensity factor on the side. But the most important thing is that this here is the rank 1 operator, and there is a little bit of extra material around it that we can work with. And of course, you have got this noise that is caused by a lot of, so, you know, it's a physical model, so the projections are not exactly the same every time, but it's close enough. So the key thing to remember for the OPU, the optical processing unit, is that you can do your transformation and output an 8-bit number, 8-bit vector, sorry, that approximates relatively well the rank 1 projection. Now, there is noise in it, and that means that if for some reason your X, the vector you project, is too sparse, then the intensity of the output will be small, and the noise will be too high for it to be accurate. So if you have if you have too small an input, then the noise will take over somehow, and this won't make much sense anymore. On the other hand, if the sparsity is too big, so if the norm of your instance is too large, then there's a clipping effect at the top because of the 8 bits restriction. That means, again, you lose accuracy. So we made a quick experiment with a vector X that you take, binary vector, and you modulate the sparsity of it. So you start with a vector full of zeros all the way to a vector full of ones. And if you remember, that projection operator is quadratic. So the output of this thing should be proportional to the squared norm of the vector. And it should be a linear relationship. And as you can see, at the bottom left, we kind of lose that, too much noise. At the top right, we lose it again because of the clipping effect I was talking about. And so it works as long as you keep the sparsity of X between 20 and 80%. Right, so now we come to the real core of the work. The sign product embedding is the function that we talked about. So if you remember, at the bottom right of my picture, there was the question that we asked, is it possible to find some function that allows us to estimate a function of the dot product between a vector and an instance, and the instance that you're considering? The answer is yes, and I apologize for the maths heavy slide here. But if you take a vector U that has to have, it has to have norm 1, it's not too bad a restriction, you can always change that, and some constant delta, you can calculate based on the sparsity of X, the size of X, the accuracy you want. You can calculate a number M that will make it such that this thing holds with high probability. So let's break this down for a bit. So on this side here, you have UX, the dot product between U and X, which is the thing you want to approximate. It's squared because, as I said, the function f is squared. So this thing you want to approximate, and you'll notice that on the left-hand side, we have this thing here, which is X transformed. So this is X in the sketch domain, U transformed as well. So U in the sketch domain. So you send them both to the same world. But U, this time, you're actually going to take the sign of every component of the vector. So the sign is not a typo, it's not a sinus, it's a sign. So negative values go to -1, positive values go to 1. So this is a vector of -1s and 1s. You project this onto that. So put X and U in the same world, project X on the sign of U, rescale it, because if M is very large, well, this is going to grow out of control somehow. You project it, you rescale it, and this actually approximates really well the quantity UX squared. And this is proportional to delta multiplied by the norm of X. So you can make delta as small as you like, provided that you can have M large enough. So if you have M large enough, you project B of X onto the sign of B of U, and that approximates this quantity well. So I hope this is relatively clear. But this is really the question that we wanted to answer from the beginning. So we have, there you go. Oh, sorry, I'll go back on this just in a second. So we have this function that we want to evaluate So sorry, this function that we want to evaluate, and it is possible to do it using the theorem that we have just exposed. Now this, to give you a quick idea of how the proof works, is that we have to first use the rotational invariance of the Gaussian, which means that we can think of x as being 1 and then just zeros, and u as being the first two components with a cosine and sine, to show that the expectation of the left-hand side term is exactly what we are looking for. And then if you fix u and x, we can use the property of the sub-exponential, actually not Gaussian, random variables to show that this actually concentrates really well around its expectation, and then extend this using continuity argument over all k-sparse vectors. So we just use the fact that we can sort of cover the space of rank 1 matrices. So like the vectors x, if you do x transpose is rank 1 matrices, we can cover this using a covering number. And then with the union bound, we can prove that this theorem holds for all u, all x's and all u of norm 1. Okay, so one last thing missing, we need some experiments to show that this actually works. So first of all, we have an experiment that shows the so if you remember the motivating example I gave with the parking lot, we have the idea of trying to detect the average in one area or the other. So imagine you have this video frame here with a circle going round on a dark background. And imagine you only have access to this image, but in the sketch domain. Can't really represent that. As I said, there's not much point. And say you want to stay in the first quadrant, and with the sketched instances, detect whether the ball is in the first quadrant or not. Well, this is possible using the result that we just presented. So if you take this product here with a vector u that you tailor to be 1 inside the first quadrant or whatever quadrant that you're looking at, and x, this actually gives you a good estimate, if it's large, that the white circle is in the quadrant that you're looking at. And we know we can approximate this taking the transformed instances and the vector u, so you transform them both in the same way. And here on this graph, well, we represent the curves normalized that show the value of this quantity, which you can see follows, it goes up and back down when the circle goes in and out of the quadrant. And so you can see that it follows them quite well. Another example is simply a classification example. So we're going to use like the standard MNIST data set, but again, only having to the sketched data. So imagine you have your training data, nice and easy, nice and simple, but for the testing, for the test set, you only have access to the sketch data and you want to classify them. So the way we do this is you take your training set. So this is the stupidest possible, the most naive possible, not stupid, possible classification method. So you take every one, make an average, every 0, make an average, and so on and so on. And then to try and find the class of a new instance, you just take the scalar product between the instance and all of the potential classes, and you take the highest one. So you just say, well, what does the new instance look most like? So this works relatively well in practice, about 80% accuracy. But here you only have access to the b of x instead of having access to the x. What instead you can do is that since we know we can approximate the square of the dot product between the average and the new instance, but only having access to the b, you just transform to the bx. You transform your sort of model transformation that you use for x, and you take the largest dot product between the transformed version of x and the transformed version of the centroid. So the centroid is like the average of every class. And look, we tried this in the direct domain, so 82% accuracy. That's when you don't do anything, you just use the normal instances. But then we tried it using the transformation with varying sizes. So as you remember, the largest m is, the more accurate the more accurate the transformation is. So with 400, you get 60%. It's better than random already. And then the higher you go, the better accuracy you get. And one last experiment we tried is say, well, instead of training the instances with the original instance, training the model with the original instances, we train directly in the sketch domain. So you transform all your instances. You have this new data set, which is a sketch data set, and you create the models of every class, but this time in the sketch domain. You sketch also the testing instances and take the largest of all the dot products. And this actually, surprisingly, gives even a better result than the original. So in the original, we had 82.7% accuracy, and now we have 83.9% with m equal to 10,000. Right, so I hope with this I have been able to convince you that it is possible to estimate functions of signal in the sketch domain after nonlinear sketching. So with linear, it was easy, it was possible. You can read the paper, it's very, very possible. But now this is possible with nonlinear projection. And I hope I also was able to convince you that this optical processing unit actually works and allows you to do this kind of work. And now for potential prospective work that we're going to try and extend this to matrices of rank 2 and above, and maybe try to apply this to a change point detection setup where you remember the parking example. Well, maybe if you give it a real DVO, is it possible to find when there are changes in the frames in some places or others? And yeah, thank you very much, and thank you to the organizer as well.
Okay, we have time for questions. Yes.
Thank you. So, I mean, in your motivation, you basically said you can work with arbitrary functions f and g. And then from what you presented, at least what I got is that you can do it for a square function. Is the actual result more general, or is it basically limited to the square function?
No, it is limited to the square function. So in this case, we work with the quadratic projection operator. And with the quadratic projection operator, it is a square function. Without, if it's the linear operator, it's just the identity function. But maybe there's others, but this work solely focuses on the quadratic operator.
So you can't say anything about like general pairs of functions f and g, what their properties would be.
Like just like this, no. But maybe there is a sort of link, but I need to define what operator you're looking at, because the function kind of depends on this.
Mm-hmm.
So I don't have an answer to this, but this would be an interesting research direction.
And how good is the optical implementation actually? Because I mean, you have a coherent source, which is the laser, and then you're putting it through this
modulator,
DMD. Yes, it will introduce actually diffraction and so on. Yes, so this will not be exact kind of projection operation. So do you have any experience with sort of a real device?
Well, I'm not quite sure I understand your question correctly, but the thing is, this projection operator, the projection machine, you can say replicating the projection operator with some tweaks that we have to take into account. I'm not quite sure what you mean by the operator.
I mean, basically the laser itself will be coherent, yes. So when it's incident on these DMD pixels, which are small apertures, it will actually include effects that are not just sort of an on-off operation, but it will introduce ringing and other kinds of things, yes, due to the diffraction. So the question is like how that affects your scalar product.
Well, I don't think it does. I think the scalar product was measured experimentally in other papers. You can go and check this. That this does, like, the output is as if it was projected by a random Gaussian. So
we can take it offline, I think.
I can comment. So as far as I know, because it is developed by Lighton in Paris, by Laurent Daudet, Igor Caron, and others, and Sébastien, I'm not sure for the first name, Sébastien Ligon. So the idea is that, of course, certainly you will have diffraction in the DMD, but the model is that after the light passes through the scattering medium, thanks to Avogadro number, you have a very good asymptotic approximation of what happens inside the scattering medium, which tells us that in the camera, each CCD pixel is going to record the square product of a projection of your image onto a Gaussian vector. So the diffraction somehow you have at the input is not especially helpful for that model. But later in the camera, there are still some imperfection, and what they do is to create micropixel to somehow minimize those distortions, like diffraction at the receiving end in the camera. So there are of course optical distortions, and somehow they manage to limit that with a few tricks here and there, to really be as close as possible to their model. Other questions? Yes, Amir?
Yeah, thank you so much for the nice talk. So I have a couple of questions, but I will postpone the others to offline discussion. So you made mention of rank 2 projections at the last slide. Could you make, I wonder if you could name a practical application of rank 2 projections?
So I think I wasn't quite clear. It wasn't rank 2 projection, it was rank 1 projection of rank 2 or more matrices.
Oh, right. Yeah.
Sorry, but the potential application, say like you instead of looking at one instance, the projection of the sum of matrices or the difference in symmetry.
Right. Yeah. Thank you.
Other questions? Yes.
Thank you for the presentation. Do you need X to be binary? Because in some of the slides you told X needs to be binary to satisfy some property.
So for the general case, for the sign product embedding, you don't, but for the machine you do. So it's really the binary restriction comes from the optical processing unit. But there's some ways to work around this. So like in the case of MNIST and the 2 experiments that we showed, it wasn't necessary because it was just black and white. But you can kind of work around it by making bit planes go into the machine. But it needs to be binary things that go in, and it comes out as 8 bits. But for the general, if you take out the optical thing, then no, it doesn't need to be binary.
And also the U matrix, does it need to be Gaussian, or can you use other?
Sorry.
In your proofs, I think you use the projection matrix to be Gaussian.
Yes, that we proved this for Gaussian matrices. Yes, yes.
But it can't be for any other.
I suppose it could be because it usually works with, so like normal compressive sensing is Gaussian, but it also works with Rademacher matrices. But we haven't done the work for this.
So can you use matrices used for phase retrieval, like the coded Fourier spectrum?
Well, I don't know the answer, but I would think so. But this works for Gaussian matrices.
Yeah, thank you.
Okay, I guess it's time to end. So let's thank Remi and all the speakers of this 2-part session.